All right, so let's start the final discussions regarding output stage. And just for the reminder, in the last lecture we saw that we have amplifiers, the kind that we had seen earlier, common emitter, common base, common collector, in which we had the amplifier or the transistor bias at a certain DC current here. And when we apply a voltage, the input voltage here, in response to the input voltage, the current also varies in a sinusoidal manner. And for proper operation, we said that what we need to do is, in these amplifiers, ensure that the transistor conducts all the time. If the transistor does not conduct all the time, then what would happen is, especially when you go towards the negative part, there would be a clipping. The transistor is not conducting. If it's not conducting, then the current is not flowing in the load, and therefore the output voltage will be distorted. So we have amplifiers where the transistor conducts all the time, and in order to ensure that the transistor conducts all the time, we have to bias it. We have to bias it at a certain non-zero current here, and the bias current has to be appropriate so that even when I go towards the negative, in this case negative voltage here, input voltage here, the current also becomes lower, but the current should remain more than zero, right? So that's the constraint in amplifiers like this here. And depending on the amount of input voltage and the kind of current that the input causes in my transistor, I have to keep ICQ above a certain value here. So that's a class A amplifier in which the current is flowing throughout the cycle and the transistor is on. Lastly, and we had seen that the efficiency of such an amplifier actually was less than 6.25% when there was a resistor. When we replace it by a current source, the efficiency we can show is less than 25%. All right, on the basis of our analysis of this amplifier, we'd seen that one of the drawbacks of this amplifier is that even when you don't apply an input, the amplifier takes power from the output here. So what we were looking for is that one of the characteristics of efficient amplifier should be that it should take power from the supply only when power is to be delivered to the load. And based on that, we had arrived at an amplifier of this kind here. An amplifier with a amplifier, push-pull amplifier here, consisting of these two transistors. And if we examine any one particular transistor, let's say Qn, so Qn will find conducts for the positive half cycle, for the negative half cycle it is off. And similarly, if we examine Qp, we'll find it conducts for the negative half cycle, for the positive half cycle it is off. So each transistor is conducting for half the cycle, and for the other half cycle it is off. And when transistors are conducting in this particular manner, we call an amplifier based on such a mode of operation of transistor as a class B amplifier. And I'd said that the class B amplifier has very good efficiency. So let's do some calculation and find out what the efficiencies are. So efficiency, as you know, is power delivered to the load divided by power taken from the supply here. So with sinusoidal voltages, power delivered to the load is the voltage V0, the peak value of the voltage square divided by 2RL. Power taken from the supply, well, the current that you draw from the supply, note that this transistor is on only for half the cycle, right? So for the other half cycle, negative half cycle, current is zero. Only for positive half of the cycle, the current that goes from here, note that this transistor is off during positive cycle. This transistor is off during positive cycle. So the current that you take from the supply starts from here and goes into the load. And therefore the current that is going from here is nothing but if V0 is the output voltage here. So it would be V0p sine omega t. That's the net voltage at this point divided by R. Of course, you recall that what happens in a stage like this is that the current does not flow until I exceed a voltage 0.7. Right now we are neglecting that 0.7 volt drop. We are assuming that the inputs are large and that 0.7 volt drop, we'll come back to that later on. So the current that flows from the supply, it flows only in the positive cycle, and the current is simply the voltage here, which is V0p sine omega t by RL here. And therefore power we can calculate. Power would be average power. I said whenever we calculate power, we talk in terms of average. So power would be 1 over T, 0 to T here, average, VCC here, and the current drawn from the supply here, which is ICN. Why am I calling it IC? Because it's the IC of N-type transistor. That's the current here. And so that's the power that is consumed here. And I'm not going to repeat it for the negative power supply. Also, we have a same expression for power, so that's why we have 2. Okay. So in the positive cycle, the current flows here. In the negative cycle, the current starts from RL and flows into the negative power supply. So same expression for power holds. That's why a factor of 2 is there. All right. That's for the 2 supplies here. So note that this is V0p sine omega t by RL, and it's only there for half the cycle. So we can easily calculate the average as PS is 2 VCC VOP by pi RL. And the efficiency then becomes the ratio of this one and this one. The efficiency becomes pi by 4 VOP by VCC into 100 here. So note that if V0p is what? The peak value here. The peak value here, if I could drive peak value here, V0p close to VCC here, so this factor can, let's say, becomes close to 1, and you are left with efficiency pi by 4, which is 78.5%. So the efficiency that I'm showing, if you can drive V0p close to VCC here. Well, we have done these calculations. How do we decide what is the highest value of V0p that we can get? Well, one of the constraints are that the collector emitter voltage of this transistor should always be greater than VC sat, which means VC sat means the collector voltage is VCC, the emitter voltage is V0p sine omega t, must be greater than VC sat. So let's take sine omega t equal to 1, and that tells VOP must be less than or equal to VCC minus VC sat. So which is fine. I can, VC sat is small, 0.2 or 0.1. And therefore, we can reach VOP very close to VCC. But I said there's one more constraint, and the constraint is that the input itself cannot exceed VCC, because if the input is coming from some previous stage, and the highest value of input is VCC. If that occurs, if the highest value of input is VCC, then the highest value of V0 would be VCC minus 0.7, so VCC minus VB. So in that case, our VOP, the highest value that you could get is whatever is the supply voltage minus 0.7 volt drop here. As I said, if you have 12 volts or 15 volts here, maybe 0.1 here, 0.2 here, or 0.7 here, maybe they don't matter that much. But if you're running it on a small supply voltage, plus 1.5, minus 1.5, then 1.5 minus 0.7, that becomes a significant drop. Okay, so one needs to take these into account. And finally, if I look at this expression, I find efficiency can be as large as 78.5%. Of course, depends on what the exact value of VCC is, and then on that basis one can calculate. But it's easy to see that 78.5%, of course, you will not be able to reach, but maybe 60%, 65% will not be too hard in many cases to reach that kind of efficiency. So we have a class B amplifier in which transistor conducts only for positive cycle, this one, and this one for negative cycle, and it delivers power to the load with an efficiency which is pretty high here. And the problem that I talked about this particular amplifier was that if we look at the this amplifier, when the input voltage is small, for example, let's look at the positive cycle here. When the input voltage is small, the transistor is not on, and nothing flows here, and that's why you see that there's no voltage here. So you need to, this voltage needs to exceed 0.7 volt for it, 0.7 or so, for it to start conducting. And once it starts conducting, note that this is a common collector amplifier. You're applying input to the base, and you're taking output at the emitter. So it's a common collector amplifier or a emitter follower. So once the transistor turns on, then the output voltage follows the input voltage here. So that's what you see here, follows the input voltage. But then again, as it gets close to 0, the transistor turns off, and again you find that it's not following the input voltage. But then once it goes into the negative cycle and the negative voltage becomes less than 0.7, the QP turns on, and so on, it repeats here. So we have a distortion near the 0 crossing. Whenever the input voltage crosses 0, we have a distortion, and for that reason we call it a crossover distortion here. And if I were to plot V0 versus Vin, if right now I'm looking at it from a sinusoidal point of view, But suppose I just start V in, I sweep V in from, let's say, minus whatever, minus 8 or minus 9 to plus 9 or so, whatever. If I sweep, then the output voltage would also vary. And ideally, what we would have wanted is, because this is effectively a common collector amplifier, each one works in a common collector mode. So we would have wanted V0 to go linearly with V in. But note that V0 does go linearly with V in. But then as you approach the 0, you find output voltage is no longer responding to V in here. And then it goes like this here. So that's the reason why we are getting this crossover distortion. All right, so that's the problem that we have to solve. But how much is the distortion? Let me just show you. For one particular amplifier, I did the simulation with plus 5 and minus 5. VCC was plus 5 and minus 5. Applied 5 volt input, right? And the crossover distortion is almost 8 or 9%, 8% or so, 8 or 9% distortion here because of this value here. When I'm running it on plus 5 and minus 5. If I ran my, design my amplifier for plus 3 and minus 3, this part would be even more significant. This part would be even more significant, and I would have even higher distortion. Okay, so the point is that even with plus 5 and minus 5, the distortion is significant, and we have to address it. So understand why is the distortion there. The distortion is there because when this input voltage is 0, the transistors, both transistors are off. I need to apply a certain input voltage, 0.7, to turn it on. So if I want to get rid of that, the way to ensure is that, well, even for 0 volt, my transistor is very close to turning on. Which means that by some means, if I take my transistor QN and I bias it at maybe 0.65 volt. So it's at the threshold of conduction. 0.65 volts is right at the threshold of conduction here. And when the input voltage comes, it adds a little bit of voltage and it turns on. So I don't have to apply 0.7. There's already a 0.65 or so applied to QN. And similarly, there's already a minus 0.65 applied to QP. If that is there, then when my input comes in, it will quickly turn on. It doesn't have to wait for 0.7 volt, and thereby distortion would fall. So the strategy is to add a battery here and a battery here, 0.65 let's say here and minus 0.65 here. If I can do that, then note that once the input comes in, this is already biased at the threshold, and once the input comes in, it would, the transistor is very close to turning on, and so it turns on easily and it supplies current, and therefore I should not have much of crossover distortion here. All right, so that's the basic idea. Add a small battery here of 0.65 or so and minus 0.65 or so. And note that when you add a battery here, when you apply a voltage here, sinusoidal, the voltage will immediately go to this particular point. Just like the voltage here goes to the base of Qn and Qp, here also the voltage will go to the base of Qn and Qp. When you don't apply any voltage here, then of course there is a certain bias. When you apply a voltage here, this voltage will go here, and this voltage will also go here because it's a fixed bias. All right, let's see how well do they work. So in this case, I took that amplifier that I showed you earlier, and I added a 0.65 volt battery here, 0.65 here and 0.65 here. Note that earlier you would have seen a distortion here. Now it's a perfect straight line. Input follows the output. Distortion becomes less than 1%. From an earlier 8 or 9%, the distortion falls to 1%. Okay, so by adding these batteries here, we've eliminated crossover, almost eliminated crossover distortion, and things are fine. I mean, in terms of distortion, the distortion becomes low. Of course, a disadvantage you would have seen. We started off with an amplifier which we said should not have any standby power dissipation. That is, when I don't apply any input, the transistors are off, and no power is being taken from the supply. Now, when I apply this 0.65 and 0.65, and I don't apply any input, because I've applied 0.65, so the transistors are actually conducting. They're not conducting heavily with a lot of current, but they are conducting. So there will be a standby current. There will be a standby current in Qn and Qp, and the efficiency will fall. All right. So what we have done is, when we add a battery like this here and a battery like this, we've arrived at an amplifier which is intermediate between class A and class B, and we call it a class AB amplifier. Class A, remember now, class A amplifier was what? In which the transistor conducted for full 360 degrees, for both the positive half and the negative half. Class B was an amplifier in which the transistor conducted for one cycle only. Now, if a transistor conducts for half a cycle and a little bit more than half the cycle, then we will call it a class AB amplifier here. So I'm showing that by drawing the current flowing through the NPN and the PNP. Note that this is the current flowing through the NPN. The red one is the NPN current here, and the blue one is the PNP current here, or either one of them. It doesn't really matter. NPN and PNP current here. Now, class B means what? Class B means there should have been no overlap between the NPN current and the PNP current. When the NPN conducts only in the positive cycle and PNP only in the negative cycle. So when the NPN current stops, then the PNP current starts. Here you can clearly see that there is an overlap. This is the zero part here, zero current here. There's an overlap between the NPN and the PNP current. So there's a time when both the transistors are on. And this is a characteristic of class AB amplifier. It's conducting for more than the half cycle. Because note that what would happen is, we said that this battery keeps it, even when you don't apply any input, the transistor is on. It keeps it at the threshold of conduction, so current is flowing. So when you apply positive cycle, obviously the transistor conducts even more. But when you go to the negative cycle, it takes a little bit of negative voltage before this Q1 turns off. So which means that it conducts for a little bit of negative cycle also, before you turn this off and then you turn it on here. So it conducts for more than the half the cycle here, and we call it a class AB amplifier here. And so this amplifier then makes more sense than the previous amplifier, where we didn't have these batteries and there was significant crossover distortion there. So the issue is, it's very simple to draw a battery here. The issue is, how do we implement the battery? How do we realize, and where do you get a 0.65 volt battery? From where do you get that? Okay, we have +5 here and a -5 here, and what we need is a 0.65 here or a 0.65 here. Now, don't get so hung up on what is this 0.65. The goal is that, note that this, I have to put a battery here and I put a battery here. The purpose of the battery is to keep Q1 and QP conducting a small current, not a very large current, a small current, so that once the input comes in, then the transistors turn on and V0 follows V in here. So the goal is to keep Q1 and QP conducting at a small value of current. And that you have to decide how much current we need and all that, that is there here. So look at, so we need about 0.65 or 0.7 volt here. Now the trouble with this is, if VB1 becomes too low, then what would happen is crossover distortion will begin to occur. If VB1 becomes and VB2 becomes too high, then a lot more current would start flowing and you are unnecessarily wasting power. So the choice of VB1 and VB2 is critical, and let's see how we implement this. So the first thing is, note VB1 and VB2. VB1 we are saying is about 0.65 and VB2 is this one here. So as I start, note that VBN, this is the base voltage of N-type, base voltage of P-type. VBN minus VBP should be about 1.3 volt, roughly. Okay. Note as you start from VBN. So if you take this as a reference point, this is 0. This becomes 0.65. This 0. This becomes minus 0.65. So the net voltage is 1.3. So we are looking for a net voltage between the base of N-type and the base of P-type, which is 1.3 volt. Would this do the same thing? Suppose I remove these two batteries here and I add this. One battery here and I add another battery. Will it still do the same thing? Note earlier when you didn't apply any voltage, 0, the voltage here was 0.65. Right? 0.65 here at the base. Is it still true? This is 1.3 and this is 0.65. So when you don't apply any input voltage here, the voltage at this point is 0.65 and the voltage at this point is minus 0.65. So either you can have two batteries like this split in this manner and apply an input voltage here, or you could have one battery here and another here and apply it in this manner here. Still, you get the same thing, 0.65 here and minus 0.65 here. But this transformation allows you to do something interesting. So, if that is true, I need 1.3 volt here. Look at this possibility. I need 1.65 volt, 0.65, 1.3, 0.65 plus 0.65 between these two. So what I do is I take two diodes, D1 and D2. I bias it at a certain current I0. I bias it at that current here, and the current of course starts from here, goes here, and the voltage, effective voltage between these two will turn out to be close to 1.4 depending on the current. So with this current I can adjust how much voltage actually appears between these two nodes here. Alright, and note that this is almost like a constant 1.3 volt battery or so, and we have Vn plus VDC over here as usual. What is this Vn plus VDC? We'll see in a minute. So you can see that the battery that was difficult for us to realize, fortunately the battery required was only 1.3. Alright, so it can be easily made using two diodes here. Using these two diodes, we can easily arrange that the voltage between here and here is 1.3. Alright, let's go forward. Okay, let's look at this one. This is what we just talked about. Let's look at this circuit here. First thing, so Qn and Qp as usual is our class AB stage. Can you see D1 and D2, two diodes that are there? D1 and D2. Realize we said when you take a bipolar transistor, short base and collector, it itself acts like a diode. Between base and collector shorted, so this is nothing but a diode, and this is also a diode. Now the diodes were biased at a certain current, I0. So the diode, let's say this is my current mirror. So if I have a certain current flowing in this transistor here, by mirror action, the same current flows over here. So the current flows here, note that here. And then we've added a PNP part here and driven our voltage at this particular point here, Vin. Can you see that what I wanted was Vin plus VDC. So this is Vin, and what is the voltage here at this point? Vin plus VDC was how much? 0.65. So I get again 0.65 or so. So this schematic that you see here, I can realize it by these two transistors connected as diodes. This is a current mirror. Any current here will be mirrored here in this part here. And instead of Vin plus VDC, we applied Vin to this transistor here to a PNP, and we automatically get Vin plus VDC, a 0.65 here. So we arrive at this particular stage here. Okay. Well, we can add a little bit more. So far we saw this. This is what you see over here. And where is this Vin coming from? As I said, this is the output stage. This whole thing is an output stage. So Vin will come from a previous stage. And I've drawn an example of a previous stage here. This is my stage. Here it was just a symbol of a source here. Now I'm saying Vin will arrive from a stage like this here. And what does this remind you of this particular stage? If you note, the signal is applied to the base. Output is taken from the collector. It's a common emitter stage. And what is the load of this common emitter stage? A PNP transistor. So it's a common emitter amplifier with a PNP load. Remember active load. If you recall, we had discussion that if you want to build very high gain, then you should not use a resistor as a load of an amplifier. You should use a transistor itself. And PNP, this transistor, is serving as a load for this NPN transistor here. So this is nothing but a common emitter amplifier with an active load, which this transistor is serving as a load for this one. So this amplifier will build up lots of gain, very high gain here. And then we have all this class AB stage here, which will, whatever voltage is developed here is now transferred to this particular part here. Because note, as the voltage is developed here, this is This is like a common collector, and this is also like a common collector. So it goes here. Voltage developed here, goes here, and then in the negative cycle, it goes through this. In the positive cycle, it goes like this. That's how your class AB stage works here. So this is the output stage here, this part here, and this is the common emitter stage with an active load. Now, the reason why I'm drawing this is, look at this particular stage and look at the stage over here. This is the part of a 741 op amp. The output part of a 741 op amp. Op amp that you're familiar with. So note that this part, they've realized the diode in slightly different manner here, but this is our two diodes here. They also have two diodes. They have a current here. This is the current, our current mirror here, and a PNP stage, a PNP here, and this is the PNP here. And so this whole part that you see here is the class AB stage here. In addition to this transistor here, they've added some resistors here. If time permits, we'll see it later on. These resistors are there for protection. If the current exceeds a certain value, the whole, the transistors, they switch off and act as a protection for the load. So that you don't accidentally short circuit. So they prevent, they sort of protect this particular device here. Anyway, so you can see this class AB stage here, which is similar to this blue and the red that you see here. And this is our common emitter transistor with the PNP load here. So common emitter transistor with a active load here. They've shown a current source. A current source is nothing but a PNP transistor. So a transistor with a current source load here. All right, this is your complete 741 op amp. So let's not panic by looking at this one. Do we now feel comfortable with this part? Right? We've just shown you a class AB stage here. These are the two diodes. This is the PNP stage. This is a current which biases the diode here. So you should not feel too scared of a stage like this now. Okay, so this is a standard class AB stage. This one that you see here is, as I just explained, is a common emitter stage with the active load here. They've just put a current source. Okay, and before this, what do I have? This transistor, as you can see here, is a common collector amplifier. The input to it comes from here. So it's a common collector amplifier and the output is taken here. So it's a common emitter stage which builds up a lot of gain and is driven by a common collector part. All right. So why have I put a common collector? Well, for impedance matching and all that we'll see later on here in between. So these two stages we should be a little bit more comfortable now. The stage that is really left is this one. Okay. This particular stage. This is the stage which is the differential pair stage here, the input stage here, where we have a little bit complicated differential amplifier. So this is the topic of the next set of discussion on differential pairs. So once we learn how to make differential pairs, then you know the differential pairs, common collector, common emitter, output stage, we have all the blocks with us. We have all the blocks with us, we can connect them up and we can make a op amp or many different kinds of circuits here. These are the major blocks of whether it's a op amp, it's a multiplier, it's a comparator. These are the elements. These are the broad elements of all the analog circuits that we'll see here. So what we have to do is next couple of lectures spend time on building differential amplifiers. Okay, and once we do that, then the whole 741 op amp one can understand why it is designed in that particular manner here. All right, so let me, output stage, let me summarize. Remember sometime back, as I said, that when you are designing a new circuit, the new circuit does not come to the mind fully formed in one shot. It doesn't happen. That you're suddenly sitting there and in one bright moment you get a whole circuit into your mind. It doesn't happen like that. What happens is you go through a process of speculation, analysis. Speculation, critical analysis. You go through that particular cycle repeatedly. Okay. So for example, let me go over it. So we have an amplifier like this. So everything starts with an existing solution. Everything starts with an existing solution and looking at it deeply as to what the problems with it are. And when we looked at it, we said one of the problems with a common collector as an output stage is that this particular stage draws power even when nothing is given to the load. And we said, let's look for a stage which perhaps does not have standby power. So it requires, actually, if you think about it, it requires a very bold thinking to say that let's have a stage like this. Somebody must have at some point said, let's not bias the transistor at all. In all previous amplifiers, before you go, all previous amplifiers, we said you have to take a transistor, you have to bias it, and then you apply an input, and the input amplifies and all that. Here we are saying, let's not bias the transistor at all. No biasing. Right? It requires a fairly, so you are saying what? You are going through a phase of, what if I don't bias the transistor? And I directly apply the input. Right? What if I don't bias the transistor and I directly apply the input? And then you find somebody can very easily reject this and say, well, if the input is very small, obviously the transistor will not conduct. But if the input is large, I have +5 and -5 sinusoidal, which is 5. Well, at least it's going to conduct in the positive cycle. So you go through that and you say, yes, it's an amplifier which will have 0 standby power, but a lot of distortion. All right, so you go through a phase of what if I bias it? What if I don't bias it at all? So you arrive at an amplifier like this. And then what you do is you analyze it critically. All right, so what are the advantages? The first thing is, don't look at the disadvantage. If you look at the disadvantage, you'll reject it and throw it away. So the first thing is, look at the advantage. So the advantage is, if you analyze it, well, it has very high efficiency. Right? The disadvantage is, well, there's no negative cycle. It just gives you the positive cycle here. But then what we do is systematically preserve the advantage and start eliminating the disadvantages. And so that led us to this one here. Well, let's add another stage here, which now gives us the negative cycle also. Right? This gives us the positive cycle and this gives us the negative cycle here. What if I add a PNP stage here? And when we analyze it, we find, yes, it's very good, but there's a problem with crossover distortion. So you analyze it and then you say, what if I add a battery? Right? At this point, we are not even asking, how do I realize a battery? If you start asking too many questions, you may reject it again. So don't ask too many right at the start. What if let's just explore. What if I add a battery here? And when we add a battery here, and we find, well, it gets rid of crossover distortion and sacrifices a little bit of efficiency and standby power, but gets rid of crossover distortion. Now you ask, how do I realize this? So then, we arrive at this particular part here. By a little bit of rearrangement of this battery here, by combining these batteries into one and putting it another, we arrive at this particular stage here. And then finally, we arrive at a stage like this. All right. So a series of steps, and then we finally arrive at a stage which we saw was something that is used in 741 op amp here. A stage like this here. All right.